hydrogen does, nitrogen does, but carbon does not. So because carbon doesn't have that fulfilled octet, it's going to share some of the lone pair. So this lone pair can be shared between the nitrogen and the carbon. So if I do the 1, I would have that. But carbon still doesn't have a fulfilled octet, so it's going to share another pair. So this is actually what would happen if I was thinking about hydrogen with carbon and nitrogen. So I'm going to have a triple bond here between the carbon and the nitrogen. Nitrogen still has a fulfilled octet. Carbon also has one, and then hydrogen also has one. Okay. Awesome. So I want to skip this for just a second because you're going to be doing tons of examples of these. I actually want to just go to formal charge. So we can determine if we're drawing the best Lewis structure or the best structural formula based on finding formal charges. Now, this was taken off of the AP Chemistry curriculum, but I don't know how you can draw the best Lewis structure if you don't do formal charge, and there's really no other method to best check what you're doing other than formal charge. So from what I've understood is if you have a Lewis structure and they ask you, how do you know it's the best Lewis structure? Because usually what will happen on a free response question, they'll give you, or they'll ask you, draw the Lewis structure for the following molecule. So then on A, you'll draw that structure. And then on B, they'll ask you, how do you know that this is the best Lewis structure? And you can show that by showing formal charge. They're not going to count you off. They'll actually accept that as correct if you show formal charge as your explanation, even though it's not technically in the curriculum. Okay, so if we want to assign formal charge, it says that for each atom, we're going to count the electrons in the lone pairs, and then I also want to count half the electrons that it shares with the other atoms. So if I have a single bond, I'm only going to count one of those electrons for that atom, okay? And then I want to subtract that from the number of valence electrons for that atom, and that difference is what we will call formal charge. So how would this look? And let me actually do this better on the whiteboard. So if I'm looking at carbon dioxide, okay, so I could have this, or maybe you had drawn one that looked like this. Both of these molecules, let me just draw a line to separate them here. Okay, both of these molecules have a fulfilled octet on all of them. This has 8, 8, 8, 8, 8, and 8. So we're good here. But which one is the better Lewis structure? That's my question. So to do that, I want to just think, first of all, how many, or what would the formal charge be around this oxygen? So we're just going to do one element at a time. And you have to do formal charge on each individual element. So I'm going to take the number of valence electrons. So for oxygen, that's 6. So I'm always going to do valence electrons minus however many that I have bonded and however many I have not bonded, okay? So I have 1, 2, 3, 4 lone pair. And then remember, we're going to do half of what it's sharing with something else. So it's sharing 4, but I want to do only half of that. So it's sharing, so really it's 2. So I have 4 unpaired and then 2 that are in that bond. So really it's contributing 6. So its formal charge here is going to be 0. Okay? If this oxygen is the same as this one, then that one should also give me 0, because this has 6 valence minus then the 4 that are unpaired plus the 2 that it's sharing here, so that's 6. So the formal charge of that oxygen is 0. Let me do the same for carbon. So carbon has 4 valence electrons minus then the 2 that it's sharing here plus the 2 it's sharing here, so 4. So when you get a formal charge of all of them to be 0, it's a great Lewis structure. So formal charge, we want to be 0. That's our goal. If formal charge is 0, usually that indicates that it's the most stable version of that particular molecule. If I come over here and look at this one now, okay, I think that's one, yeah, okay. So if I come over here and look at this one, so on this side, if I just want to focus on this oxygen, so we know that we have 6 valence electrons for oxygen, and then I'm going to subtract however many electrons are around that particular oxygen. So I have 1, 2, 3, 4, 5, 6 unpaired electrons, plus 1 extra electron that it's sharing here with carbon. So I actually have 7 electrons that are around that. So that gives me a -1 formal charge around this particular oxygen. For carbon, so for carbon I have 4 valence electrons here, and it has 1, 2, 3, 4 that it's sharing. So that gives me a formal charge of 0 here on that carbon. But now let's look at this oxygen. So oxygen we know has 6. It has 1, 2 unpaired electrons plus 3, 4, 5. So this actually gives me, on this oxygen, a formal charge of a +1. So all over here, I had a nice formal charge of 0, meaning that everything had some type of balance to it. But now over here, I have an oxygen over here that has a -1 charge, and an oxygen on this side that has a +1 charge. So it should make sense to you. Oxygen is going to be more electronegative. It's very electron greedy. So the fact that I have in my molecule one of the oxygens as being a +1 state is something that's going to create a lot of instability in that molecule, because oxygen would very rarely, if ever, want to have any type of positive oxidation state, okay? So this is just a good way to check if you have drawn a Lewis structure in the best way possible. Okay, so the best Lewis structure is the one with the fewest charges, or let's say that there's no way that I could not go without having a negative charge on one of the atoms or elements in my compound. So in that case, I want the negative charge to be on the most electronegative atom, okay? So let's say, for example, I give you these 3 options. If I were to give you these 3 options, and I went ahead and wrote the formal charges above each of them anyway, if you want to go back and check, you're more than welcome to. So on this first one, I have a -2 formal charge on the nitrogen and a +1 on the oxygen. Doesn't seem the best to me. On this one, nitrogen has a -1, but the others are 0. Well, oxygen is more electronegative than nitrogen, so this one also doesn't make the best sense in the fact that if oxygen's more electronegative, it should be the one carrying a negative charge. So then over here I have my last option, where nitrogen and carbon have a 0 formal charge, and oxygen, the most electronegative out of these 3, has the -1 formal charge. So the best one, or the best option in these 3, would be this third choice here, and that's because the formal charge that's the -1 corresponds with the most electronegative element, okay? If I'm looking at the last 3 here, so what I would like you to do for your homework, I also am going to post some practice problems with doing some more with the lattice energy, but I also want you at the beginning of class to tell me which is the dominant Lewis structure of these 3, and I want you to tell me why. You can tell me why by showing me with formal charge. That's how I want you to explain for me, okay? And then I'm going to have the answer posted in the video that you're going to have at the beginning of class on Thursday. So Thursday is going to work by, you're going to have like a little small video kind of finishing up covalent bonding, because I really want to talk about that and finish up the notes with that. And then you're going to have Lewis structure time in groups with you making Lewis structures with the pretzels and M&Ms, okay? And then after you're done, you can eat anything that you have used. After that, you're going to do a little bit more practice with Lewis structures, and then you're actually going to use the rest of the class time to finish pre-lab, and then write your actual lab procedure in your lab notebook, so then that way hopefully you won't have homework on Thursday, okay? And then on Friday we'll do a lab, and you will totally have homework on the weekend. Okay, so we're going to stop here. And we'll continue, no, I don't. I just want to keep going with resonance. Oh man, we need to do resonance really quick. I'm just kidding. Okay, guys, for resonance. So if we're talking about ozone, I'll try to be as fast as possible. If we're talking about ozone, then this is the Lewis structure that we would draw for ozone. But do I have to draw it this way? Or could I have the double bond also on the other side, with this side being the single bond? I very well could. So this gets us into a resonance structure. So even though we will draw, let's go back to that one. Even though we draw a structure for ozone that looks like this, what we actually find in nature for ozone, it's so cool. When we have measured ozone, we have found that the bond lengths on either side of the oxygen molecules are actually the same. They're the same length. And that is because in real life, we don't have one Lewis structure versus another. So before, let me go back really quick. Let's go here. So ozone I could draw this way. And I realize I drew that really big. Or I could draw it like that. Okay, so because I could draw them either way, the double bond could be here, single bond here, or double bond here, single bond here. What we find in nature, it's actually a hybrid of the two of them. So usually I think about the electrons as kind of being evenly distributed between these two oxygen molecules that surround that central oxygen atom. So it's really just, and I'm only drawing this because that's sometimes how we think about them, that the electrons are really just a nice evenly distributed among that, or between that central oxygen. So when we find in nature ozone, we find that the bond lengths are the same. So ultimately, a resonance structure, or one Lewis structure really doesn't do justice. I could have ozone looking like this, we could have ozone looking like that, and it's really a hybrid of the two that we find in nature itself. When we have more than one resonance structure, then this is how I want us to draw, or if we have resonance structures, I want you to draw them this way. I want you to draw a double arrow on either side, or an arrow that has a head on each side, just because it could be this one, and it could be this one, and it's actually a hybrid of the two. If you have more than two of them, and especially if you have one that's charged, you're going to draw brackets around that Lewis structure, and then the charge on the outside of that bracket. And then arrows in between to represent that you have resonance structures, okay? So that would be my nitrate ion. So if we think about resonance, we can think about it like this. I could have one resonance structure here, another resonance structure here, and in real life, I'm actually just going to get a blend of the two. So I may have a blue here, a yellow here, but really what I see in real life is going to be green. So for example, resonance structure here, the different resonance structure here, and then this is the overall ozone molecule that I see. It's a blend of the two. It's a synthesis of the two. Okay, and then we'll draw resonance structures when we're doing our practice with our M&Ms and pretzels in a little bit. So we'll actually stop there, and then we can talk about this when I come back for Friday, or when we don't have a lab. Okay, awesome. I will see you guys on Friday. If you have any questions during your class time on Thursday, I will have my phone on me the entire time. So again, if you have anything or need anything, let me know. I will see you Friday. Bye, guys.